a 30, 60, 90 triangle and a 45, 45, 90 triangle, doesn't matter what the lengths are, the sine, cosine, and tangent will always be the same. And a 45 angle will always be right to cosine will always be right to will always be 1 and negative. So the idea of the unit circle is let's make the radius as easy as possible. Instead of thinking of it as x, or instead of it could be 22 and 20, a radius of 22 or a radius of 2, let's make it a radius of 1, and these special angles will always have the same values. So the unit circle is just taking these values and putting them on a circle with a radius of 1. So that means our special angles that intersect the x and y axis become ordered pairs that we should be able to say, if this is a radius of 1, what's the ordered pair going to be at 0 degrees or 0 radians? Which means at 0 or 2 pi or 4 pi, anytime you're there, the x coordinate can always be 1, the y coordinate will be 0, and you can use that for your ratios of your trig functions. Just going to spread out here. But suppose to say pi halves. If I was up here at pi halves, and this is a radius of 1, then this ordered pair would be zero, 1, right? So instead of having to think about it as 0y or whatever, you can always think of it as 0, 1. And over here at pi, right, it's still a radius of 1, but the point where that circle would intersect the x-axis is now on the negative side. So that's going to be negative 1, 0. And I kind of ran out of room. I don't know why I didn't put 3 pi halves down here, but I'm going to go ahead and add it here. 3 pi halves is kind of like the one that we did in our notes yesterday that we talked about. You could call that point 0, negative y. Well, now we're going to say, let's just do it for the unit circle, because 1 is a great radius. Because if 1 is the radius, what would the ratio for sine now become? Right, we're trying to get away from SOHCAHTOA, so instead of thinking of opposite over hypotenuse, we want to think of it as x, y's, and r's. So what's our ratio for sine using x, y's, and r's? Y over r, but if r equals 1, the sine is y over 1, which means the y coordinate of the point is always the sine value, which is pretty awesome. Which means the cosine, what's the ratio for cosine? X over r, but if r equals 1, then we can think of cosine as the x coordinate, which is really cool, because that means if you know the ordered pair, if you know the xy point on the unit circle, you know that the x coordinate is cosine and the y coordinate is sine. Flipping them over, cosecant, flip it over would be 1 over y instead of r over y. And again, we have to say that y can't equal 0. And secant is 1 over x, where x can't equal 0. And the great thing is if you know tangent, you still know tangent, because tangent didn't have r in it anyway. Right? Tangent is opposite over adjacent, or when in the circle or on the coordinate plane, that's y over x, where x is 0. Cotangent is x over y, where y is equal. So what we want to do is we want to talk about those special angles, 45 degrees, 30 and 60, and what would those ordered pairs be if I drew in the angle? What would the point be, the x and the y point? So then instead of having to draw triangles every time, I can use the unit circle. But the unit circle values come from the triangle, right? So I drew the lines in for you this time, right? The first one here, what if I divided that first circle up into? There's 8 parts, so how much is each one though? 45 degrees, or in radians, pi fourths. So let's label that first. That's what we did the other day. I'm going to label it on the inside because we're going to put points points on the outside for the x and the y pair. So this is my 0. I'm going to go by radius. Okay, so I'm going to say pi horse. I have 3 pi horse. Pi. You want to put your degrees next to it, you could. Halfway between pi and 3 pi half. The 8/4 gets you back to 2 pi. You could put those same ordered pairs that we said already. Like we know this is the point 1, 0. This is the point 0, 1. Negative 1, 0. And this is the point 0, negative 1. What we want to talk about is what is this point in between here? And with the radius of 1. And so we could kind of derive this. We could say if the radius is 1, what would the two sides have to be so that we could get a radius of 1 for a 45-degree angle. And it works out that remember x is the sine of a 45-degree angle. The cosine. So we can say it's square root of 2. And remember that the cosine and the sine at 45 degrees are the same. So it's also square root of 2 over 2. So this is why people like the unit circle over the triangles once you get down all right out. Because now you don't have to draw triangles. You can just memorize this ordered pair. And you can use reference angles to get to the rest of it. In quadrant 2, is the reference angle going to still be pi horse? So my ordered pair should be the same, except for in quadrant 2, what's going to happen to the x coordinate? It's going to be negative. You could also use your idea of reflection. If you took this and you reflected it over, all that changes is your x becomes negative. So that means that 3 pi horse is negative square root over 2. Then I'm here at 5 pi fourths. So the reference angle is still going to be 45 degrees. My triangle is going to be the same. It's going to be the same distance away. But what happens to my ordered pair in quadrant 3? They're both negative, right? It's the same point on that circle reflected over. So it's the same ordered pair, the same reference angle, only now it's negative running over 2, negative right. And in quadrant 4, same point, right? That's why I did it separately before you do it all together at once. You can see where it comes from. Same point, only now in quadrant 4, which one's negative? So y is negative. Which means you don't have to feel like, if you've seen that unit circle that's on the other side of the page of your homework here, right? It looks a little overwhelming at first. But once you see where the numbers come from, you don't have to memorize it all, just go a little bit, and then use the reference angle for your reflections to get there. What about, yes? Because, okay, if we drew our triangle in here, right, and we're saying it's a radius of 1, you have to think about your ratios of a 45, 45, 90 triangle. What would the sides have to be in order for it to fit the ratio of square root of 2 over 2, or 1 over square root of 2? So normally we say that if this is x, this is x, this is x squared root of 2, right? Well, we know in the unit circle the radius has to be 1, so we know this is a length of 1. So you have to solve for x and say, what would x have to be in order for the radius equal 1 to make a 45-degree angle? So like that means that this would have to be, this was 1 over the square root of 2. If I took that times the square root of 2, does that make this 1. This would be 1 over square root of 2. I just rationalized it, first of all. So square root 2 over 2 is the same as this. So that's kind of where the point comes from, because the radius has to be 1. Another way you can think about it is we just talked about in the unit circle. If you're doing the unit circle, the sine and the cosine will always just be the y-coordinate and x-coordinate. So another way to kind of prove where it comes from is if I took any 45-degree angle, and I call this x, and this x over 2, the sine of that would be x over 2. Right? And the cosine would be the same thing. So if you want to use that way to prove it, you could say, well, the ordered pair has to be what the sine and cosine would be. But I think the better proof of it is to just solve that. If the radius is 1, what would the sine be? Okay. Alright, we're going to try to get this written out before you leave. What about this one? This one's going by what increments? Pi 6? So I'm going to do this again. 0. Pi 6. I don't know what makes more sense to you to count by pi 6 all the way. It really works every time. But also remember the 6 are always on either side of the x-axis. The thirds should always be on either side of the y-axis. So this is pi thirds. This is pi halves. This is 2 pi thirds. This is 5 pi 6. This is pi. This is why we did this the other day, because now that we're doing a unit circle, we've got to be better at our angles because we're moving past that and we're adding points now. So you don't want to have no clue where the angles are when we're talking about. And just keep going around. This is 7 pi 6. This is 4 pi thirds. 3 pi halves. 5 pi thirds. 11 pi over 6. Because back to 12 pi over 6 is 2 pi. And again, we could solve these triangles because this is a 30, 60, 90 triangle now. Pi 6 would make this a 30-degree angle, but we know the radius is 1, which means the x and the y point now become, if the radius is 1, the x has to be what is the cosine of a 30-degree angle, and the y becomes what is the sine. So it works out that the sine of pi 6, or the side opposite in our normal 30, 60, 90 that we think of, is radical 3 over 2. But again, if the radius is 1 now, that makes the x-coordinate radical 3 over 2. And the y-coordinate is 1. And if you want to rewrite your 1 zeros and your 0 ones, you can. I'm just going to leave them off because it's the same. They never change. So here's what's really great, and I'm going to do this in 2 steps. All of these pi 6, 5 pi 6, 7 pi 6, 11 pi 6, are they all going to be the same reference angle? Which means just like over there, if you know pi 6, you know the ordered pair of all the sixths. You just have to change the signs depending on which quadrant you're in. So that means in quadrant 2, I know it's just going to be negative radical 3 over 2, 1/2. And in quadrant 3, at the sixths, I know they're just both going to be negative. So that's negative radical 3 over 2, negative 1. And at the 11 pi 6, it's going to be radical 3 over 2, negative 1. And again, we could derive that by saying if you drew a 30, 60, 90 triangle and you said the radius had to be 1, then the only way that works is if this value is radical 3 over 2 and this value is 1/2. Did I do that right? One half. Sorry, do it backwards. Opposite is one half. Yes. Once you go to the unit circle, sorry to go back. Go. Okay, here's what's extra great, or maybe this is what's the hardest part about the unit circle. In a 30, 60, 90 triangle, do you agree that the sine and the cosine just switch when you switch from 30 degrees to 60 degrees? Because the opposite and the adjacent side switch places. Which means for pi thirds, all you do is you switch the ordered pair. So instead of radical 3 over 2 and 1/2, your adjacent side is now your opposite side, and your opposite side is now your adjacent side. So it's 1/2 radical 3 over 2. Which is nice, but also it's really easy. And we just flip it. Go all the way around. So this is negative 1/2 radical 3 over 2. This 4 pi thirds is negative 1/2 negative radical 3 over 2. And 1/2 negative over 2. I'm never going to make you choose triangles or unit circles. Eventually, most people jump on the unit circle bandwagon because it seems easier. I'm a triangle person. My teacher never taught me unit circle, so it's taken me a lot of years of calculus to be a fan of the unit circle. But triangles always work too. So I don't care. I'm never going to make you on a test like repeat the unit circle. But on a test without a calculator, I'm going to make you tell me values at all these angles. So we put this together to make the unit circle, and the more we practice with it, the more that we can practice doing calculus. So let me show you. It kind of seems overwhelming. Because when you put it together, it's even more overwhelming, but let me show you the trick that makes people like the unit circle. But first of all, this is why we didn't do it all at once. This is the unit circle because it has 0 and it has your pi fourths there right in the middle, right? But then it also has your increments of 30 degrees and 60 degrees, which means the smallest one here is my pi sixths, and up here is my pi thirds. So let's see if we can do the first quadrant, and then maybe for homework I'm going to see if you can repeat the rest of it. Most people are thinking about flipping it over using the negatives and positives. So remember that this is our point 1, 0. This is our point 0, 1. So you'll just don't fill it in yet. But what I want you to do is for each of these, I want you to just make an ordered pair. Like, make an ordered pair, leave a parenthesis, a comma in the middle, but don't fill it in yet. So I want to show you how, if you know this trick, you'll get the first quadrant right. And if you know the first quadrant, it's really just flipping it over to all the positives and negatives. So it's just repeating itself for all of it. There we go. Alright, here's the trick. If you start at the upper inside one, like the first coordinate there, you're just going to write 1, 2, 3. 1, 2, 3, and then 2 options. I always do 1, 2, 3, and I go back up to the top and I count backwards. 3, 2, 1. 1, 2, 3. 3, 2, 1. Or some people like to go 1, 2, 3, and then move over and count back up. 1, 2, 3. I don't know. Then you're going to put everything over 2, because everything's over 2. So it's 1/2, right? So put everything over 2, make it a fraction. So we got 1, 2, 3, 3, 2, 1, everything over 2, and then you just take the square root of all the top numbers, remembering that what's the square root of 1? Square root of 1's 1, so that doesn't change, but you just put a square root sign over everything that's not 1, and you just completed the first quadrant of the unit circle without having to feel like you memorized a bunch of stuff. And if you know the first quadrant, do you agree that everywhere there's a pi 6, if you know your angles, everywhere there's a pi 6, you're just going to repeat that, but change the signs depending on whether x is positive or negative. And all the pi 4s, you're just going to repeat it, but change the sign. And all the pi 3rds, you're going to repeat it and change the signs depending on what quadrant you're in. So You never have to really like fill out the whole unit circle. You just have to know the first quadrant. So fill that in for tomorrow, and we'll start on the same slide tomorrow. Okay. I'm going to show you the hand trick or the hand trick.
I just want to see if it's clear in Ashton, right? Cool.
Right?